A couple of announcements for you. Make sure, if you haven't already, make sure you demo Lab 2 in the lab to a TA so we can get the grades recorded for those. We assigned Lab 3 at the beginning of last week, and Lab 2 wasn't actually due until yesterday, right, because we extended it, so there was a week overlap between those two. But you still have 3 weeks for Lab 3. Quiz 3 is assigned and it's due next Monday, so you have a week for that. And the first exam will be in 2 weeks. And it'll be, I'm just going to give it on Moodle, and you have a week to take it. So you'll have, you can take it any time between October 24th and 28th.
Did you say the exam's on Moodle?
Yeah.
Okay.
So the exam will cover everything we've covered up to this point, which is going to be the RISC-V ISA, Microarchitecture, which is what I'm going to talk about today, fixed point arithmetic, logic circuits, hardware description language, and system Verilog. Okay, so quiz 2 was due last week, and so I'm just quickly run through that. The first question was, consider the following system Verilog module. What is not a problem with the module? So when you look at that, the first option there is C is double driven, and that is a problem because you can't assign C with the assign and with the always comb. So that's not an answer. B is no sensitivity list for the always statement. That's okay if you have an always comb, because the always comb considers any input in the sensitivity list. So that's not a problem, which means that is one of the correct answers. Yeah, there's more than one.
Oh, really?
Yeah. Actually, this is a bad question, so I gave everyone credit for it. Okay. But there's more than one correct answer.
Okay.
C is cannot use an if statement in system Verilog. That is true unless the if statement is in an always block. So that's not a problem, so that's also a correct answer. D is use of a blocking assignment in an always statement. That's also not a problem. You can, obviously, in an always statement, you can excuse me, you can choose whether you use blocking or non-blocking assignments in an always statement, so that's not a problem. E is cannot combine an always com and an assign in one module. That's not a problem either, because that's fine. And F is the always block has no default assignment for C. That is a problem because if the value of any of the inputs here, which would be A, B, or just A and B, I guess, right? If A or B changes, it activates that always statement. And if B is false, right, or if it's Z or undefined, then C will not get assigned. And so that'll create a latch. And generally, you don't want to create latches. You guys see that? Makes it so. In other words, you'll end up with memory in there. And actually, I think the compiler will actually give you an error, even if you try to compile that, because the compiler will notice that that's a latch. And obviously, that wasn't your intent because you said always underscore com. So that's actually an error. So there's actually 4 responses that are correct. It's implied by the question that only one of them is correct, but in fact there's 4 of them that are valid. So
did you say that the always com is an always com statement in general is always sensitive to any input to it? Any
input, yeah, which means anything that appears on the right-hand side of an assignment statement or any signals that are part of a condition.
If we were writing Verilog, could we specify more things to be sensitive to, even if it's redundant?
You could.
Okay, just wondering.
I don't think it would make any difference, though.
You would probably do like always star and then additional steps.
Well, you could just say always at and then list them in the parentheses. I don't know.
List whatever.
Yeah.
Always come.
Yeah. Okay, question 2 was consider the Verilog module below. How many input signals are specified? This one's really easy. It's just a matter of counting them. And so the input signals here are clock, reset, load, and seed. But the last one listed is an output. It's a little confusing because you don't have input or output specified for reset or load, right? Because they inherit the fact they're inputs from clock. So it's an easy question, but it is kind of confusing the way the syntax is set up. So the answer here should be clock, reset, load, and seed. So there's four inputs, one output. Okay, there's another system Verilog module. Assume the module is reset with a reset pulse at the start of execution. What is the value of state in the first 3 cycles? So in cycle 0, which is the reset value, it's 100. So the always underscore FF resets state to be 100. And then as we go to the next cycle, state bit 2 is going to become 0, right? So state bit 2 previously is 1, right? Remember, you're numbering these bits from right to left. So state bit 2 is 1. That's going to become 0 in the next cycle. And actually, it's going to stay 0 forever until we reset. And then state 1 is going to be whatever state 2 was in the previous cycle, which means state 1 will inevitably become 0 forever as well, but there'll be a 1 cycle delay. So state 1 will start out as 1, having inherited that from the reset version of state 2. But then after state cycle 1, it will just become 0. And then state 0 is the old state 1 or the old state 0. So if either one of state 1 or state 0 was a 1 in the previous cycle, then that bit will go to 1. So, obviously cycle 1, you're looking at 0 or 0, so you have a 0 in cycle 1. And then in cycle 2, it's 1 or 0, so it'll become 1 in the next cycle. So the answer here is 100, 010, or 001. This one was a little vague because I said, what is the value of state in the first 3 cycles after the reset pulse? I was including the reset cycle in there as well. Okay, give the value of signal A in the first 3 cycles after reset, so very similar question. So this one starts out with a reset of 101, and then, now this one, here we're combining a blocking and a non-blocking assignment, which is something I told you shouldn't do. But you can do. You're allowed to do it, as long as you're not using Verilator, apparently, as I recently learned. So what that means is that the second statement is going to see the new value of the first statement immediately. So it's kind of like taking the sub-expression A shift left by 1 bit and substituting it into the A of the next line. That's essentially what's happening there. Okay? So in cycle 1, A is going to be first shifted to the right by 1. So 010, it's going to get shifted to the, to the left rather, to the left by 1 bit. And so that will become 010. So, basically we drop that first 1, and then we have a 01, and then we shift in a 0. So 101 becomes 010, and then we XOR it with 111, which just flips all the bits. Right, so we shift, so 101 becomes 010, but then it becomes 010 again because we invert all 3 bits by XORing it with 1, right? And then, so it'll just stay at that value. So basically, it just stays at 101 forever. It never changes. So 101, 101, 101. Okay, what's the problem with the following code? Well, this is supposed to be combinational logic, but it has a combinational cycle or combinatorial cycle, meaning that A is being updated, but then the new A is a function of the old A, but there's no clock. It's not clocked. So you end up just with this, basically you end up with an oscillator. You can do something like, this is actually a very common thing to do. This is a counter, except in order to make it a counter, you need always at pos edge clock. right? You don't want to do it without the clock. You want it to be clocked. You want the clock to control the rate at which it counts up. Okay. Always statement should be combinational but has a cycle, so the answer is A. Okay, then we have a test bench, and so I'm giving you the test bench and I'm asking you what function is being tested. How would you know that? Well, you look at the inputs and the expected output, and from that you can build a truth table. So the output is 1 if the inputs are 1 and 1. The input is 0 if the inputs are 0 and 1. Okay, so this is a little tricky because notice how I set A and B here at the beginning. So the inputs are 1 and 1. But then after the first test, I only change A, which means that B stays the same. So the inputs here are 1 and 1, and the second input is 0 and 1, in which case that should be a 0. All right, so 1 and 1 gives you true, and 0 and 1 gives you false, starting to look like an AND gate. Now I change B in the third test, we end up with a 0, 0 because I change B to 0 and leave A as 0. And the expected value output is 0. Okay, that's still consistent with an AND gate. And then finally I change A to 1, that gives me a 1, 0. And the output is expected to be 0. So it looks like an AND gate. Pretty much always gives you a 0 unless the inputs are all 1. And oh, sorry, yeah. So yeah, the solution here would be to, use the test vectors to build a truth table. What are the first three values of A generated in the snippet below? So this one is 5 bits now. So in cycle 0, we reset values 1, 0, 1, 0, 1. And then after that, we do some bit manipulation here. So in cycle 1, we get the old value of A0, which is 1. Starting from left or right. So starting from most significant to least significant. Here with this concatenation. When you do these curly braces, it's always ordered from most significant to least significant. So we start out with the old A0, so that's going to carry this guy down to this guy, comes down to the next row and gets put here in A bit 4, right? The leftmost bit. You guys see that? And then we get 2 copies of A1. So A1 is 0, so I'm going to put 0, 0. And then not A3. So A3, that's going to be a 1. Now I'm starting to lose my place here. So I guess the A3, I'm going to take an inverted A3 and put it into bit 1, right? And why bit 1? Because it's second from the left here in this squiggly concatenation thing. And then the least significant bit is the old A2 XOR the old A4. So we're going to go 2, 4, XOR. 1 XOR 1 is 0. You see? So the solution here is to basically go through this line using the bits from the previous row, from the previous cycle row. Okay? Now, likewise, for cycle 2, we're going to start out with the old A0, so A0 from cycle 1, right? So we're going to take that 0 from here and bring it down to here. So, again, the row up all the way to the right now goes in the first bit. And then 2 copies of A bit 1. So A bit 1 is 1, so 1, 1, right? So that 1 gets duplicated, those on bits A3 down to A2. And then complement A3, so that 0 gets complemented and becomes a 1 there. And then we XOR bit 2 and bit 4. So 2 and 4, 1 XOR 0 is 1. You see how I did that? Okay. All right. Okay, that's it. That was it. There was just 7 questions on that quiz. Okay, so moving forward with the new material. Last time we talked about registers and RAMs. They're both memory They're both memories. Registers have no address. They just have a single location, whereas RAMs have an address. RAMs can have multiple ports that you can, each port allows you to do a read or write in one cycle at the same time. So if you have 3 ports, you can do 3 accesses to that RAM at one time, and like on the register file, you're going to be able to do 2 reads and 1 write. You guys with me? That makes sense? Okay. RAMs can have whatever geometry in terms of width and depth. The depth is the number of unique addresses that are in there, the unique locations, and the width is number of bits you read or write at one time, right? The depth is usually listed first, and the width is listed second. So if I have a 1024 by 32, right? What is that? 4 kilobytes, right? Because 1024 deep and then 32 bits wide is 4 bytes. So that's a 4 kilobyte RAM if I say 1024 by 32, right? Okay. Okay, so that's, so the problem though with RAM is that the way you define RAM is a little strange, because RAM is something that requires kind of multiple lines to define. So in this case, we first declare the RAM array as logic 31 down to 0, mem 8191 down to 0. So this is a 8K by 32 RAM. Remember that when you declare it, you have to swap the width and the depth from the standard way of specifying that, right? So we have width first, then depth, right? So we have that's the actual like storage for the RAM. And then I have to define my read ports and write ports. So I've got a read port down with this assign statement because it's an asynchronous read port. So I can use an assign. And then my write port has to be in an always FF. So writes have to be synchronous, reads can be synchronous or asynchronous. So what does that mean? That means that if I want to write a RAM, it's going to take me a cycle. It has a 1 cycle write latency. If I want to read, if it's asynchronous, it's a 0 latency. I can read in 0 cycles. But if it's a synchronous RAM, it's going to take me 1 cycle to read. Now, how does this relate to your project? Well, your instruction RAM is going to be a synchronous read, which means it's going to take 1 cycle to read an instruction, which is why you have a fetch stage, right? The fetch stage in your pipeline is essentially waiting to read an instruction because it takes 1 cycle to read the instruction, and therefore the fetch stage is 1 cycle. You guys with me? Now, in parallel to that, though, in fetch, you're also going to be incrementing your program counter, right? As a counter, you're going to be ticking up the program counter. So you're going to be doing those 2 things at the same, concurrently in parallel inside the fetch stage. Okay. And then I also have this initial block that initializes the memory. You don't always have to have that. That's optional. But in our case, we're going to put it in. That's the way we're going to load the program on our CPU. We're just simply going to initialize the instruction RAM with our program. Okay. Any questions about that? Now, if I wanted to add a read port, I could add another assign statement here that reads another element of data out with a separate address. So if I had another address and another read data, I could add another read port, right? In fact, I could add 10 more read ports if I want. The problem is that you'd never be able to, I don't think you can synthesize that on FPGA. When you actually develop real RAMs, there's generally limits on how many ports you can have, but System Verilog doesn't care how many ports you have. Okay? Likewise, I could add write ports just by replicating that always, but of course also giving it different addresses too for each write port.
Can you talk more about initializing the RAM?
Yes, yeah. So the initialization is, this is the same. The reason I didn't talk about this much was because I covered this for the test vectors when I talked about test benches. It's the same mechanism. So basically, there's this $readmemh is what's called a PLI function. It's one of the standard functions that you can call in Verilog. And there's a readmemb and a readmemh depending on whether the data in that file is binary or hexadecimal. But either way, it's just a text file. I don't know if there's a way to read a binary file in. Probably. I've never done it, but these are text files that you can open in a text editor and read, right? And basically it's just a values listed. Generally they're on different lines, but it turns out that the only thing that separates the values in that file is white space of any kind, so you can actually put tabs or spaces, whatever you want. Generally though, you just have one value per line, right? So in RARs, when you compile, or when you assemble your RARs program and you dump it to a file as a hex file, it just coincidentally writes a file that's compatible with this function, which means that all you have to do to load your program is to generate, you have to assemble in RARs, and then just say file export, is it export? It's file dump, yeah, dump memory, I think it is, dump memory, and then you just say I want to dump the program, and it'll very conveniently be in a format that'll be read by this line of code without you changing, you don't have to change the file. It's just a coincidence. It just happened to work out that way, luckily for us, right? So you go into RARs and you dump your program as a hexadecimal text file, and then you combine that with readmemh, and this will load your program into your instruction RAM. I mean, it doesn't have to be an instruction RAM. I mean, we used to initialize the register file too back in the day. In an older version of this course, we only had the R-type instructions in the first lab. We didn't have I-type, so there's no way to initialize a register at all. And so we had to initialize the register file to put any kind of initial values in there at all, right? Nowadays, we tell you guys, like in this lab, you're going to do R-type and I-type instructions. Why? Well, because by having I-type instructions, then you can initialize register values with the code. You don't have to use this to initialize for your register file, but the instruction RAM still needs to be loaded so you can have your program in there. Does that make sense? Okay. And by the way, I should also mention, one of the complaints I always get in this class, and I've never found a way to solve it, is that there is a huge jump in difficulty between Lab 2 and 3, you're going to find. Obviously, Lab 3, you're designing the CPU. Lab 2 is trivially easy. Lab 3 is very difficult. And there's really no better way to make that transition. In the past, we tried to have you design an ALU or design just the fetch stage or design just the register file. We tried different approaches, but none of them quite worked out, because if you're just designing the fetch stage, it's so confusing. Like, what am I doing? Like, it was hard to see how that fits into the whole CPU. And if you just design an ALU, well, that was kind of trivial. And at one point, we had you just designing the test bench for the ALU, and we deliberately put a bug in there that you had to find with your test bench, but everyone hated that because it was boring and you had to come up with all these test cases. It's tedious. So as a result, we go from you doing a 7-segment decoder to now designing a whole CPU in the span of one lab. And you might say, well, that's insane, but there's just no better way to do it. And like I said, we used to try to restrict the instructions more too. Like we said, oh, just R-type instructions, but then you had to worry about initializing registers, so it was a hassle. So yeah, we are aware that there is a big jump. And we try to help you out as much as we can, but there's just no good solution to it if our goal is to have a working CPU by the end of the semester. Okay? But we're here to help. If you need help, we're in the lab. We have, come to our office. I'm here all day, every day. Okay. Okay. Then last time we talked about synchronous versus asynchronous read. If this is confusing to you, the bottom line here is that the instruction RAM is synchronous. Why? Because, well, we want a fetch stage. We want to design a pipeline CPU, so we're going to make it take one cycle to read an instruction, and therefore the instruction RAM is synchronous. However, the register file is asynchronous because we want to be able to read a register and do an ALU operation in the same cycle, and therefore it must be asynchronous. We need a 0 latency read on the register file, but a 1 cycle read on the instruction RAM. So they're both RAMs. Of course, the instruction RAM is read-only. Your program can't modify the instruction. We don't want self-modifying code. That's a recipe for Skynet. Computers shouldn't be able to program themselves. But the register file is read-write. Okay, and there's the register file. So we give you the register file. It's pretty much what I just got done showing you. It's a little bit more complicated though because there's 2 read ports and 1 write port. You'll notice that the read ports are made with assigns. The write port isn't always FF, so you know it's an asynchronous read. And the other thing we did was we hotwired it, so if you read register 0, it spits out a 0. You can still write register 0 because this line of code will allow you to write register 0. But if you write to it and then you subsequently try to read the value you wrote, you won't get it. You'll just get a 0. So any writes to 0, get basically lost. They're not accessible. And then this second option here is the bypass path. And this is required for pipelining. If you have an instruction that's writing a register at the same time another instruction is reading it, it means that you wrote a register in one instruction and then in the next instruction you read that register, right? Well, obviously if that happens, you want to get, the second instruction should get the up-to-date value, right? But the only way for that to happen, if it takes one cycle to write, is for this bypass. Otherwise, you'll get the stale version, you'll get the stale copy of the register. You guys with me on that? That makes sense? Do I don't have any markers here. So, like, what I mean by that is if you have so let's say you have like add x1, x2, x3, x4, and add x5, x2, x4. So if you have something like this, okay, so if you have an instruction sequence like this, if you have a pipeline CPU, or in 3-stage pipeline CPU specifically, this first guy is going to be writing register 2, while this next guy is going to be behind it in the pipeline reading register 2. So you want this guy to get the updated value from that guy, okay? And that's just because it's a and I'll talk more about how the pipeline works here in a minute, but that's the reason for the bypass path.
And you said which line was the bypass line again?
That was, it's part of the read port. It's this one right here. It says, so you're going to assign read data 1. Okay, if this first condition is false, meaning the read address is not 0, then you go to this is the else, right? Because we're using a nested ternary operator. This says if read address is equal to write address, in other words, I'm reading on port 1, I have 2 read ports, but if port 1 read address is equal to what I'm writing, I only have 1 write address, but I have 2 read addresses, so I have to handle these separately. So if my first read port is clashing with my write address, they're the same address, and write enable is 1, meaning I'm actually actively writing, then I'm going to take the write data, which is coming in this input, and I'm going to hotwire it to read data 1. So I'm basically going to take this input and I'm going to connect it directly to the read data 1 output without going through the RAM. So this will bypass the RAM. In other words, this part, this second part, actually does not even use mem. Because it's like, don't even worry about it, because if you read the memory, you're going to get the old value, right? And then if neither one of these conditions is true, then I just say mem of read address, right? So that's the bypass. Okay, and the ALU we give you, the code is here. The important thing to understand about the ALU is it's a combinational logic circuit. There's no memory in here at all. There's no clock input. There's no reset input. It's purely combinational. You give it an A and a B, 2 32-bit inputs, and an op, an ALU op. And then, depending on what the op is, it's going to do a function on A and B and spit out the result on R, right? Additionally, there's a flag called 0 that says if the result of the ALU is a 0, then I'll also assert this 0 flag, which is useful for resolving branches. Is it? Wait a minute, let me double check that. Let's look at the code and make sure that's right. 0, yeah, assign 0 equals, if R is 0, then assign 0 to 1, otherwise 0, yeah. So that's what this line of code does right here. It's just one little assign statement that takes care of the 0 flag. You guys with me? Okay, so I think there's like 13 operations, so some of these are redundant, but we have all the basic things we need, I think. Bitwise logical and or XOR. We've got add, subtract, and multiply. And for multiply, we have multiply low and multiply high. The multiply high has a signed and unsigned version, just like the RISC instructions do. And set less than and shifts. That's pretty much it. So the pretty basic set of operations. Okay. That's the code for it. And again, we're going to give you this as part of the project skeleton. Okay, so in Lab 3, we want to implement these 22 RISC instructions. Now, the problem here is that these span 3 different instruction types: R-type, I-type, and U-type. You guys probably never heard of U-type because they didn't have U-type with MIPS. That's new for RISC-V. So R-type, you guys remember R-type? R-type is R-type is an instruction that has 3 registers: 2 input registers, 1 output register, right? So that's like basic number crunching stuff. I-type is when you have an immediate, like a constant, that you put in the instruction. Useful for incrementing a register, or loads and stores and branches also require an immediate for addressing purposes, right? And then U-type. U-type is, I don't know what that stands, like upper, it's load upper immediate. You might say, well, wait a minute, hold on. We had load upper immediate with MIPS too, but yet we didn't need a whole instruction format for that. What gives? Well, the reason for that is because for whatever reason, I don't know why, RISC decided to shrink the immediate field to 12 bits. If you guys remember, it used to be 16 in MIPS. So when you had a load upper immediate, you could load the upper 16 bits. And if you just had an add I or an or I, you could load the lower 16 bits. Nice and simple. But now they've split it differently. Now we've got a 12-bit immediate for all the I-type instructions. And then if you want to load the upper bits, you got 20 bits for the load upper immediate. And of course, 20 plus 12 gives you 32. Now think about that though. Like that means anytime you add, like say add I only got 12 bits. I can only put a value from negative 2048 to positive 2047. I only have 4,096 unique values that I can put in this immediate. That kind of sucks. I mean, that's going to be bad if I ever need more bits than that, right? Well, obviously, if you need more bits, then you can use more bits, but then it gets translated into a pseudo instruction. So the assembler will end up adding one of these load upper immediates in there for you to be able to load more bits than just. So 12 bits is your limit for one instruction. If you need more than 12 bits in a constant, then it gets split into multiple instructions that load a register. You guys with me? So what ends up happening is we had to have you implement the load upper immediate, because even if you don't put this in your program, the assembler probably will. So you don't have a choice, right? So you got to support this. This is hugely important. It comes up a lot. It's used quite a bit in pseudo instruction expansion by the assembler. So we had to have you do that, and then the I types are needed for initializing registers, right? You got to start out. You got to have some hard-coded values that you can initialize, especially if you don't, since we don't have a memory. We don't have data memory here. We don't have loads and stores. So we're relying on the register file exclusively for our memory. Okay. All right. So also, there's this weird instruction called CSRRW. So we used to handle this differently. We used to have a special register. I think it was register 30. Any instruction that read from register 30 would pull in the data from the switches on the FPGA board. And if you wrote to register 30, it would push that data out to the hex displays. So otherwise, register 30 was off limits. Like the real register 30, you couldn't access, right? So what we did was we implemented the I/O behavior over here in the register file. We had an additional logic down here in this always FF, the write port. We augmented the write port and the read ports to have some special stuff in them for, register 30, which was our I/O register. But that was confusing, and also no processor actually works that way. But luckily, when we switched from MIPS to RISC-V has this new instruction called CSSRW, and it's intended exactly for this purpose. So we decided to use it. So the actual name of this is Control and Status Register Read and Write. It's a little bit confusing though, because it's called Read and Write, and it really means that. It always reads and writes. It does both. So you can't just write a control register. It forces you to read a status register, and you can't just read a status register, you have to write. So what it does is it takes a status register, which they call a CSR, and it puts it effectively into a temporary spot T. And then it takes one of your general purpose registers and it kicks it out to an output I/O register, control register. And then it takes the temporary value and puts it into one of your registers. So what it essentially does sort of is swap in a way. Except it doesn't actually swap, because the destination register doesn't have to be the same as RS1 rather, right? So in other words, you can specify if you had the same register for these two, it's a swap. It basically takes what's in your register file, puts it out as the output, and take whatever's coming in the input and puts it in your register file, right? But you don't have to do that, because you can have two different registers specified here, right? So that's a problem though for us, because we don't always want to update the hex displays when we read the keys or read the switches, right? Likewise, if we read the switches, we don't necessarily want to update the hex displays. So how do we get around that? Well, so we're going to cheat a little bit here. So the way we're going to get around it is the RD field, and I think RISC I think the RISC people intended for you to be able to get around it. You can just specify register 0 as the destination, right? Which I mentioned, you can write to register 0, it just has no impact on the state of the computer, right? Likewise, you can use register 0 as the control and status register, right? So what that means is that if we want to read the switches, and I never remember this, I always have to look this up. So you might have to refer back to this. If you want to read the switches, in other words, the switch on the FPGA board, you want to take the value of the switches and suck them into your register file. You just specify 0 as the register you want to, the second operand is the, there's the legend up there, RD, CSR, RS1. So CSR, if that's 0, we want to write the state of the switches into register RD. Right, so in other words, whatever the user is putting in on the FPGA board, we're going to bring that into register RD, whatever register you want to use for RD. And then if you want to write the hex displays, you specify 2 as the I/O register, and then X1, which is the value you want to write to the hex displays, and then you just use register 0 as the destination register in your register file. So basically, these are the two like recipes, for either reading the switches or writing the hex displays. Make sense? In terms of your code, right? Now, the only issue here is if you actually use these in RARs, I think it'll give you an error. Charles used to have a modified version of RARs that got around that, but I don't know what happened to that. But it's not a big deal, because when you're testing your code in RARs, you can just replace one of these with, you could replace this with a load immediate, right? And you can just comment this one out, right? But when you deploy this on the FPGA board, you're going to put those back in. Yes?
So the value in the register X1, when we're writing to the 7 segments, there's 8 7 segments total.
Right.
That's 7 bits for each. I think 7, maybe 8.
But you're going to include your decoders too. So your 7-segment decoders only require 4 bits per hex display.
Yeah.
Right, and then they decode it to 7 bits, right? So you're right. So there's 4 bits each, so there's 8 of them, and 4 times 8 is 32. So with this instruction, the second one, the second instruction, you can write all 8 hex displays in one instruction.
Okay.
Right, but the value, the 8 values in the register, in this case register X1, is going to be treated as a vector of 8 values. Right? So there's a vector of H values which are each in a 4-bit chunk, right? A 4-bit field. So there's 8 4-bit fields inside register X1 here that will get translated into 8 separate values. So again, think of it like a vector. You've got a vector of 8 elements inside here, and in one instruction you can push those out to the 7-segment displays. But again, you have to use your decoders though. Your decoders are an integral part of this, because otherwise you're right, you wouldn't have enough bits. You'd need 56 bits to do it. Likewise, this value you'll read in the switches, now there's only 18 switches. So you're going to have 14 zeros and then 18 bits from the switches. Okay? Is that clear? Okay. Okay, so your top level design then will be basically, you're going to have the FPGA and you're going to put your CPU on there, and your instruction memory is going to be a RAM, on-chip RAM. You might say, well, instructions are usually off-chip, right? Yeah, in a real computer, but we're simplifying this. We're just going to keep the instruction memory on-chip like they do in an Arduino. And then your 7-segment decoders, as I mentioned, will be part of this as well, right? So the only data coming in from outside the FPGA, so the external world will be bringing in the clock, which comes from an oscillator crystal, a piezoelectric oscillator, and then key 0, which is the rightmost button. There's 4 buttons on the board. That's going to be our reset input. So if you push key 0, we want to reset the CPU. Basically make it reboot. That's our reboot button. Okay? And then the switches, there's 18 switches, those will come in. And then the only thing coming out is the 56 bits of the 8 7-segment hex displays. Now, if you don't have that, the compiler will optimize your entire design away. Your whole design will disappear, because the only way that the compiler will generate any hardware at all is if there is a path from inputs to outputs through, and by the way, if there isn't a path through the inputs, from the inputs to the outputs, through every circuit on this thing, it'll optimize those circuits out that, that don't have any impact on the outside world, right? It's very sensitive to that. So a lot of you will run into this problem, I'm sure, where you compile your design and you put on the FPGA and it's just dead. It's like a paperweight. And you're like, what's going on? Well, chances are, if you look in the resource usage from the compile, it'll say 0, 0 LUTs, 0 RAM, 0 DSPs, right? Because the whole design got optimized out because for some reason there was a breakage in the path from inputs to outputs. Usually, from even a small typo. Like you literally type one, like for example, hex. If you have a typo in the hex display, you put lowercase x instead of uppercase x, boom, gone. Design, the whole thing gets optimized out, okay? So you have to be careful with that. Just be aware of that. Okay, so everyone always asks in this lab, how do I get started? The tricky part is like, where do I begin with this? So this semester, I decided to kind of give you the starting point and make it very explicit. And I know Soyash talked about this on Wednesday in lab. I think he demoed this. Did you talk about it on Friday too, or just on Wednesday?
No, just
Wednesday. Okay, so if you're in the Friday lab, you didn't hear it, because Soyash said no one was paying attention on Wednesday because they're finishing lab 2. But that's okay, I'm going to talk about it now. So basically, if you look in the skeleton, your CPU skeleton has, I think there's 4 total system Verilog files in the skeleton to begin with. There's a sim top and a top, which you guys have seen, right? So sim top is the test bench, and top is the top level thing that goes on the FPGA, right? That's your FPGA design, top. And then you're going to have also ALU.SV, that's the ALU that I mentioned we're giving you, and the reg file 32 by 32.SV, we're giving you that. So I think there's 4, right? So when you start this project, the first thing you should do is create a 5th file, which is CPU.SV. Okay, so start with that. Just start with CPU. Now the question is, okay, so here it is. So start with the CPU. So the CPU will have initially, it'll just have a clock input and a reset underscore n. Now the underscore n is important because the buttons on the FPGA board are active low, which means when you push the button, it's a 0, and when you release it, it's a 1. So if we're going to use that button as our reset, you're going to want to treat the reset as an active low or a negative logic, right? And that's what that underscore n is. So we're going to have an underscore n there. By the way, that's very common too in FPGA design. Usually resets are active low. Okay, then what? Obviously, I haven't added the switch input or the output for the hex displays, but we'll add those later. What's the next step? The next step is the instruction RAM and the clock. I mean, the PC, program counter, right? So the clock is kind of the heartbeat, and the program counter is kind of is going to be a counter sequence that's going to pop out, and then that counter sequence goes in the instruction RAM. It's going to give you an instruction sequence. So you're going to get a stream of instructions once per clock cycle, right? And that's what we expect to start with. Once we have that, then you guys can bolt stuff onto that. You know, you can put, you know, control logic on there. You can connect the instructions coming into your ALU and your register file. It's real easy, but you got to start out with a stream of instructions. So for that, let's see. What I started out here with instruction RAM, 31 down to 0, 4191 down to 0. So this is a 4 kilo entry, 4,000 entry deep, 32 bits wide RAM. Now, if you're getting graduate credit for this class or honors credit, in the last project we're going to expand that to 64 bits wide so we can fetch and execute 2 instructions per cycle. But right now we're just assuming one, you know, in order 1 instruction per cycle. Obviously, to speed up CPUs, you got to do more than 1 instruction per cycle. It's called superscalar. And if you really want to go fast, you don't even execute them in order. You execute them in whatever order is fastest. Yes?
Sorry, what did you say was superscalar?
More than 1 instruction per cycle, issuing more than 1 instruction per cycle. So we're going to issue 1 instruction per cycle here because there's only 32 bits coming out of the instruction register, the instruction RAM. So we only have the ability to read 1 instruction per cycle, which is going to ultimately limit the speed of the processor, the throughput, how fast we can churn through instructions. Okay?
So we're not superscalar.
No, not unless you're in the graduate, or unless you're getting graduate credit. Lab 5 is the graduate version where we're going to expand it to have 2 instructions pop out. Okay, and then we have the initial statement that loads the program. I called it program.rom, and actually, Soyash, is there a requirement, are we requiring a certain name for that?
.dat.
What?
.dat.
Program.dat?
Yeah.
Okay. Sometimes we require a name for that file. You can call it whatever you want, but sometimes we ask you to name it a certain way to help our grading scripts. I don't think there's a requirement this semester, but I'll let you know if there is. But it's not important, just whatever you call it file. Extension's not important, you know. Okay, so then we have the program counter. Now, you'll notice that I call it program counter underscore fetch. There's a reason for that. So this is a pipeline CPU. It's only 3 stages, but we have to keep track of the stages, what signals are in each stage. So the program counter is in the fetch stage, which means that if you're simulating your CPU and you look at the program counter, that's the address of the instruction that's actively being fetched in that cycle, right? So that's just, it's going to make it easier to debug. Likewise, we're going to have instruction underscore EX, which is the instruction that's in the EX stage at that time. So that way, when you look at a moment in time, you'll see the program counter of the instruction being fetched and the instruction value of the instruction being executed. That's what those suffixes mean. Okay, so then pretty much you just have an always underscore. Oh, I forgot an underscore FF there. Sorry, and I just wrote this, so there we go. Not a big deal. You don't need it, but. Always underscore FF at pause edge clock. If reset n is 0, then we're going to 0 the PC fetch, and we want to 0 the instruction. because we don't want, when we reset, we want to put a no op out as the first instruction to come in, okay? That's not true, sorry. What I meant to say is you want to zero out the instruction that's being executed in the second stage of the pipeline. So basically you're going to blast out whatever instruction would have normally been in execute, right? I'm going to zero it, okay? And then otherwise, when I'm in steady state operation, I'm always adding 1 to the program counter once per cycle, and then I'm going to basically just take whatever's in the RAM at that address, I should say at the old address, right? So I'm calculating the new PC, but I'm using the old PC to grab the instruction at the old PC value, right? Okay, so the instruction, what you'll end up with is just a program counter counting up and the instructions rolling out. Now, when the program counter hits the value of 4091, in the next cycle, it'll roll back to 0, right? And we're going to take advantage of that because in this program, the program we write is going to have to continuously run over and over again, but we're not implementing branch instructions yet. So because there's no way to write a loop, we're going to take advantage of the, the odometer rolling back to 0 to create a natural infinite loop that the program will run in. And so what this will do is make the whole thing interactive, because anytime you flip a switch on the FPGA board, the program will instantly react because it's running in an infinite loop that only takes 4096 divided by 50 million seconds. Every 4096 50 millionths of a second, the program will finish and run again, right? Which is really fast. Even, it's a slow processor, but that's, imperceptibly fast, right? So it'll give the illusion that, flipping a switch on the FPGA board will produce an instantaneous response. Okay? Okay. All right, so once you have the CPU.sv done, and you can just use my code, we need to hook it into the rest of the infrastructure. So this is something that, I don't know, you may disagree, you may not like it, you may want to do it a different way, but this is the way I do it. I have the CPU is instantiated within top.sv, right? So if you look at top.sv, you just have to add 1 line of code for that, which is CPU, my CPU, and then connect the clock input to the clock_50. Clock_50 has to have that special name because it's a pin, whereas, clock is more of a generic, CLK is more generic. And then reset N is going to be connected to key 0, right? So that'll connect the clock input and the key input into the CPU. Now here's the other thing though, the 7-segment decoders. This is the part you may not like or you may not agree with, but I usually put the 7-segment decoders in top.sv as opposed to being in CPU.sv. Now that's up to you, but I always consider the decoders kind of external to the CPU. So that way the CPU is going to have an output port, I call it IO2 just because IO2 is the CSSRW name that we gave the hex displays. But you'll have a 32-bit output coming out of the CPU, which you'll feed into the decoders 4 bits at a time. But that'll happen inside top.sv. If you want. If you really want, you can push those into the CPU too if you want. But I think if you do that, then you're going to have 56 bits coming out of the CPU going directly to the hex, right? Likewise, the CPU will have an input called IO0in, and that will be the switch, right? So we'll bring the switch in from the outside world into the top, and then from top we'll send it into the CPU, right? So you'll have these mappings inside of SymTop, because SymTop is a test bench that goes around the top, and that has no inputs and outputs because it drives the clock and the reset for simulation purposes. So these little dots that I have here, these dots are like, they terminate inside the SymTop, basically, right? Make sense? Yes?
So this top and SymTop are completely different from the one we did in Lab 2?
No, they're the same. You can reuse them.
Oh.
Yeah, you can reuse them. They're the same.
Okay.
Because like if you already have the decoders inside top, then you can just reuse that code. That's fine. Yeah, the intent was for you to build on your old code.
Okay.
Okay, so that's the way I would set it up. Now, so top.sv, you only have to add one line of code for this. In SymTop, it's a little bit more complicated because I have to instance top, which I call DUT, design under test, and then I'm going to wire, oh, I screwed that up. That should be clock 50 is actually clock, oh, no, I take that back, no. Apparently it's just called clock in SymTop, yeah. It's called clock 50 in top, but I think in SymTop we must have just called it, because I took this from code that was working, so it can't be a bug. It's just called clock. In SymTop we have something called clock, but then in top we refer to as clock 50 because that's the actual name of the clock. So we connect those, and then the hex displays are connected, and then switch is connected, and then key. Key is lowercase key, because in the SymTop, for whatever reason, I just have it as lowercase. Why? Because I set key. I have a simulated key inside SymTop. So I simulate the key. This is how you're going to put a test input value in, right, when you simulate. You'll set key, well, that actually key is for resetting. Switch is your test input, right? So in SymTop, you can set this switch to be your test value, and then when you simulate it, you should see model sim, eventually output the output value that you're expecting. You guys with me? So this is a simulated key, a simulated switch, and a simulated clock that you're putting in SymTop. But then when you take top and slap it on the FPGA, then it becomes real. It becomes the real devices. Okay. Okay, so let's talk about this CPU a little bit more now. So hopefully you guys remember from 2.12, because this is something that should have been emphasized a lot, that in the MIPS CPU there were 5 stages of execution. Fetch, decode, execute, memory, and write back. And the significance of these is that each one of these operations is the most work you can do in one clock cycle. Right? These operations were sized to be performed according to the critical path delay. They're all sized so their critical path delay would be whatever your cycle time is, right? So it's basically, you take an instruction and you break down an instruction and the CPU decomposes it into 5 steps at most, right? Not all of them are used for every instruction. Okay, so instruction fetch is basically saying one cycle is devoted just to fetching the instruction, which in our case we have that to do that because we have a synchronous read on that instruction RAM. Decode is reading the registers out of the register file and decoding the control lines, the control signals, doing a lookup in the control signal table. You guys with me? Sometimes other stuff happens too, like sometimes branches are resolved in decode. The branch predictor might be in decode, right? The branch target predictor might be in decode. There's other stuff you could put in decode, but that's essentially decoding is like the first step you do once the instruction arrives. And then execute is when the ALU is invoked. That's when you do your number crunching. And then memory is if you have to go out to memory for a load or store, and then write back is when you write the result back. So if you have a 5-stage pipeline, those are your 5 stages. However, in our case, we're going to collapse the decode, execute, and memory into one stage to simplify things. So now, by the way, if you have a single cycle CPU, you do all of those in one cycle. And in fact, some of you probably have experience with single cycle CPUs. The ARM Cortex-M series of processors, M standing for microcontroller, which is what you have in the Teensy, a lot of the hobbyist kits. Some of the Arduinos have this, right? These are single cycle CPUs, meaning that the instruction, all 5 stages happen in one cycle. But the trade-off there is that the cycle time is really long. Those CPUs are only like 40 megahertz, right? Which is fine, like if you're doing something really low power, like if you're using a Teensy for something, like a sensor node or something, right? But we want a faster clock, so we're gonna do pipelining. But like I said, we're going to combine decode, execute, and memory into one stage. And actually, as I mentioned, we don't do anything in memory because we don't have a data memory. Okay, does that make sense? So we have 3 stages. We have fetch, and then we have execute, which does everything in the middle, and then we have write back. So every instruction has to pass through 3 stages. But the confusing part, that part's easy to understand. Okay, I got it. But the confusing part is that those 3 stages are in 3 different cycles, which means that every instruction has a 3-cycle latency. It takes 3 cycles to get through the CPU, right? However, during each of those cycles, we have 2 other instructions being executed at the same time, but at a different stage. Yes?
So it looks like decode and execute are asynchronous. So they would...
Yes, decode is asynchronous because the register file is asynchronous. So we can do decode and execute in one stage only because the register file is asynchronous.
And then the execute result is also asynchronous, straight to memory?
Right, because that's the ALU. Yeah, the ALU is asynchronous. Well, it's combinational asynchronous, no clock, not clocked. But we still want to split, like we want to put write back in a separate stage, right? So in order to do that, we're going to have to put our own delays in here, our own pipeline registers. So whatever comes out of the ALU is going to have to be captured in a register, right? So we can move it to the next stage. So that instruction will have data that will pass into the next stage, right? So you're going to have a few pipeline registers to convey data from cycle 1 to cycle 2. Not many, I think there's only 2, something like that. There's not very many. Okay, so you don't have to have a lot of pipeline registers. But this just gives us an excuse to learn how to use registers, essentially. Okay, so as I mentioned, though, the complicated thing is that you have to keep in mind that we have instruction-level parallelism here in the sense that there's 3 instructions that are always in progress. We're always executing 3 instructions at a time. Right? So while we're in cycle 2, while we're fetching instruction n plus 2, we're executing instruction n plus 1 while we're writing back instruction n. Right? Assuming that n plus 1 and n plus 1 and n plus 2 are in that order, in that execution order. Does that make sense? You guys with me? Okay, so it's basically just keep track of what signals are in which stage and delay values from one stage to the next when you need to. Because just putting a register in there, just a plain old register that says always underscore FF at pause edge clock, new value equals old value, that will effectively push a value from one cycle to the next. Okay, so let's talk about how you actually put these things together. So this is the fetch and decode, and I've already given you a lot of this already in the code that I gave you for the CPU. So the program counter, and oh, by the way, I broke a couple rules here with these block diagrams because this program counter has a loop. It's a clocked loop, so it's fine because there's a register. PC's a register. But notice that the data flows, it goes to the right and then it comes back to the left. You're not supposed to flow data to the left. But anyway, the instruction memory is here. The program counter is here. There's a little incrementer circuit and it goes into the address on the instruction memory. Now, do you have to have a special line of code that corresponds to this +1? No, remember in my code I just had one line of code, did the PC and the +1 in one line of code, right? So this graphical representation is just symbolic. The hardware will look like that, but if you go back and look in how I actually did that, oops, skipped it. Yeah, so pretty much that is just implemented right here in this always FF, right? We got the program counter, incrementer, and the instruction RAM all is inside this this code, right? So you can see that the block diagram in the behavioral code are not the same. I mean, they do the same thing, but they're 2 different ways of showing what's going on in there. Structural versus the behavioral code. Okay, so yeah, so basically you just have the program counter that just mindlessly increments because we don't have branches and jumps yet, so it just always marches forward by 1. Oh, and you might say, wait a minute, why by 1? I thought these are 32-bit instructions, which are 4 bytes, not 1 byte. These are 4 byte instructions. Yeah, I forgot to mention that we're just going to make the instruction RAM word addressable. In reality, real computers use byte addressed, which means that they actually increment the program counter by 4, not by 1. But I mean, there's no point in doing that here. We have control over the RAM. The RAM is, we know it's a 40, what is it, a 4K by 32. It's 32 bits wide. So if you increment it by 1, you advance 32 bits, right? So just made it word, again, just to make it simple. Okay, but like again, if you remember from 212, that was incremented by 4. Okay, then the instruction pops out, which I call it instruction EX. And this is the part where you have to take the instruction and you have to decompose the instruction into fields and feed each of those fields to a different spot. So this is why the instruction encoding is why you need to know this, right? So a lot of the people that teach 212, they don't really cover instruction encoding because they figure, well, when would you need that? When would you need to know? Well, this is when you need to know it. When you're actually designing a CPU, you have to be able to take all the bits and kind of route them to where they got to go. So this is obviously different from MIPS, though, because remember, RISC-V and MIPS have vastly different instruction encoding. And I used to have the MIPS one memorized, but I don't have this memorized. This one is way more confusing than MIPS. So you may have to refer back to this, right? Because the encoding is wackadoo. You know, the opcode, for instance, remember it used to be the first 6 bits of MIPS. Now it's 7 bits, and it's the last 7 bits. It's the rightmost 7 bits. That's the opcode. And then they have Func3, Func7, and CSR. What's that all about? Well, these are weird function fields. I don't know why they have 3 bits and 7 bits, and I don't know how they decided any of this. But CSR is the 12-bit immediate field that's used for the I/O register for the CSSRW. So anyway, those are the 4 fields that are needed for the control unit, because those are the 4 parts of the instruction that tell us what the instruction is trying to do, right? So we're going to take those 4 and route them into the control unit. Now let's talk about the control unit a second. What is the control unit going to be? What's it look like? What is it? Well, it's just a lookup table. It's just a big truth table. But how do you implement it? How do you implement a truth table? Well, it's up to you. You can use an assign statement with a trinary operator. You can use a case statement, although I think it would be difficult to use a case statement because, oh no, no, it's not. You can use the case Z statement. Remember, the case Z allows you to specify don't cares. So you could use a case statement. I use just an if then else is what I use for this. Now, do you put the if then else in your CPU? Or do you create a module for it, which is what I'm implying by having it in this box, this blue box? Is there a module? Yeah, maybe. I don't. I inline it. But that's just because I'm just too lazy to wire up. See, the problem is when you add a module, you have to then wire it up, right? So you have to create a new file. You got to put the stuff in the file. Then you have to figure out what the names are in the module versus the names are of the things coming in. Right? So then you have to put the module in and wire it up, and if I don't have to, I don't do it because it's just too much work when I can just inline the code with an always com. I could just stick an always com and have the code. Now the problem with that though is you violate the rule that my old programming 2 professor told us, where it says you should never have a function in any program that doesn't fit on one screen, which at the time was 24 lines because we had old text terminals that were 24 lines. So they used to teach us that you shouldn't have any function that's more than 24 lines. You probably, if you extrapolate that to Verilog, it means you shouldn't have a module that's more than 24 lines of code. But I don't know, no one follows those rules anymore. But that's up to you. You can decide how you want to do the control unit. But essentially, it's going to be some kind of basically if then else, case statement, whatever. It essentially just looks at those inputs and it resolves them to control. Now you might say, wait a second, you don't have any outputs on that thing. Not yet. I'll show them in a minute. Right now it's just inputs, right? I'm just showing what inputs go in, okay? But basically it's just it's a lookup table that takes inputs and spits out the relevant signals. Then the register file, which we gave you, and that, of course, that is a module. You have to, I mean, you could inline that. You could copy and paste it in here if you want to inline it, but I might as well just keep that as a module. Now that has read address 1 and 2 and write address. Read address 1 is bits 19 down to 15, and I never remember that. Again, that's the weird, crazy RISC-V fakakta encoding they use. Read address 2 is 24 down to 20. And then write address is the RD. Again, this corresponded to the RS1 and RS2. Remember in MIPS they called them RS and RT. Never figured out what the T was. But this is RS1, RS2. These are the two source input registers. Then you have RD, which is the destination register, and that's bits 11 down to 7. Now this one, though, this one is problematic because the destination register isn't used when the instruction is executed. It's used when the instruction is written back. So as a result of that, you have to put a pipeline register there. You have to delay. You don't want to write back in this cycle. You want to write back in the future cycle, next cycle, one cycle into the future. So you put that register in there that will delay the write by one cycle. Right? So I'm going to read in the execute stage, but I'm going to write in the write back stage, which is in the future. One cycle and the next cycle. And it's simple. You just, now here's the weird naming thing though, right? Obviously this is called instruction EX 11 down to 7. But then after you add the register, what are you going to call it? Instruction WB 11 down to 0? Well, you could, but then you'd have to delay the whole instruction. I usually just call this 5-bit signal regdes write back. But you can call it, again, you can call it whatever you want. But basically, same signal, two different names, but also phase shifted by one cycle relative to one another. Okay? Any questions about that?
When you say you use a register to pipeline when it's written back, is that one register implemented as like a tri-state buffer?
No, just always underscore FF, pause edge clock.
Okay.
And then you say regdest equals instruction EX 11 down to 7.
And so
that's all that is.
Putting it into the register and taking it back out.
Yeah. Yeah. Now again, that's assuming you're inlining the register. You could create a register module. Some people in this class do that. They want to have a register module, and they could just you could feed it into the register module and have an output. I just inline it. I just have one line of code and always in fact, I usually have an always underscore FF, and I group all my registers into one always statement just for convenience. Right? But that's basically just an always FF is what that is, that register is. It's just a clocked assignment, essentially. Okay, so let's see, that was, okay. So now, so this slide shows the same thing, except now we have, oh yeah, sorry, I forgot. So this is something that is also optional. Last year, I had a TA who was, he liked to work very closely with everyone, and he tried to come up with ways that he thought were helpful, hints, right? One of his hints was that instead of feeding the instruction directly into the control unit, you can use a decoder which renames all the fields. Now, why would you do that? Well, it basically makes it easier to debug, because you don't have to try to figure out what the fields are in model sim, right? Because in model sim, the instruction is just 32 bits. How are you going to figure out where the registers are? You're going to have to figure out what the number, and like I said, I haven't memorized those. I don't know what the RS1 field is in RISC-V. I have no idea. I have to look it up. And if you're trying to do that in model sim, it's frustrating. So if you create a decoder, you can just rename through an assignment statement. Well, you have to declare the signal and then assign it. You can rename. So he created this thing called a decoder, which allows you to take each of these little fields that I've shown here, opcode, you can have a signal called opcode, which is just a sign from instruction EX 6 down to 0, right? That makes it easier to debug. I leave that up to you. Again, it's not something I do because it's an extra step. I usually just, keep this slide handy and I can look up what the bits are. But it is easier, I agree with them that it is easier to debug it if you're trying to track down a problem, if you have a decoder that actually just renames the fields into more readable forms. Okay? Okay, that's what that is. Okay, now I mentioned just about out of time. This is the last thing I'll show. I already talked about this. This is what the window looks like when you export your RARS code to a hexadecimal file. By the way, they call it hex file, which is misleading. It's a hex file in the sense that it's a text file with hexadecimal values in it. But if you ever see an Intel hex file, which is a standard file type, that's a binary file. So sometimes when you see hex file, you don't know if it's a text file or a binary. This is a text file though, right? So anyway, you just go to dump memory to file, and you have to say text section and hexadecimal text, hit OK, and you'll get your program out. Now, by the way, when you're debugging though your code, your CPU, you're going to want to have RARS open at the same time as you're debugging so you can figure out what to expect inside your CPU. Right? It's good to have them both, to see RARS updating the registers and then they have it happening in your hardware. Okay, sounds good. We'll see you next week.